Hi there and welcome to another video from Hegarty Maths. It's Mr. Hegarty here, and this is the sixth and final video on critical path analysis for Decision Maths A-Level. What I wanted to talk about in this final video is I want to show you how to draw and interpret a scheduling diagram. Before I get there, I just want to talk about what scheduling is. So scheduling. This is the process of assigning workers to your project. Okay, so it's a process of saying I've got 3 employees. Employee 1, you do these activities. Employee 2, you do these activities. And employee 3, you do these activities, for example. And there's some assumptions that you need to make when scheduling. And the following assumptions are the ones that you need to make. Each activity can only be completed by one worker throughout that activity. Once an activity is started, it must be finished by that worker as well. And also, once a worker finishes an activity, they are immediately available to do another one. To do another activity. Okay, so the process of scheduling is to assign your workers to these tasks in order that your project gets completed in the smallest possible time, the most efficient time, and so that your employees are being used effectively and not sitting around with nothing to do. So that's what this is all about. So what I'm going to do is I'm going to start off with the example we ended with on video 5. We had this activity network and we drew the following Gantt chart. Now I want to schedule this, so what I want to do is assign workers to each of the sets of tasks. Now, when you're doing this, so this is my Gantt chart here. And what I'm going to do underneath, I'm going to draw a scheduling diagram just straight underneath here. Now, one worker could do activities A, B, C, F and H. Okay, so you would need one worker to do the critical ones. Okay, so I'm going to put them at the very top and I'm going to say that's worker 1. Now the reason they could do these is they can do each of these activities, and when they finish one they start another. So you would need one person to go throughout the 26, I think it was days in this case, and work out and complete all those tasks. Now the other activities you're going to need other workers for. So what you might want to do in this case is you might want to keep B. Let's see who we can assign to another worker, worker 2. So what we can do is, in this case, we can say that B can get started on, worker 2 can get started on project B straight away, on activity B even, straight away. No harm with that. So there we go, worker 2 can get started on that. Now D and E must happen after B, so it's got a choice of which one to do from that stage. Do D or do E. So for example, let's do D. There's no harm in doing D here. So we do D at this point here, and D is 6 long. So 1, 2, 3, 4, 5, 6. Okay, so worker 2 can do that. Now E, the thing about E is, E has some flexibility. It can start at 3 and it can go all the way up to ending at 18. So we could shove it along some, but no matter if we shove this along, you can see here, if we shove this along right to the very end, you can see that there's going to be some overlap there. It can't happen after D. Okay, it can't happen after D. So we're going to need a different worker for that. But G, which happens after D, can slot straight in there. So activity G in this case, starting at 9, ends at 14, we can slot that in here, like that, activity G. So just to label the ones we put in, we put B here, we put D here, and we put G here. But unfortunately now we need another person, which is a worker 3, to complete activity E. And it doesn't matter where activity E goes, as long as it happens after B. So activity E, and it finishes before H starts. So we can just do E like this. E is how long? It's going up to 3, up to 30, it's 10 long, like that. And worker E can do that there. So worker 3 can do activity E. And that's our scheduling diagram. It's almost like we're compacting these together and to try and make the least possible workers. Currently, if I had just left it like that, I need 1, 2, 3, 4, 5 workers. I've shoved them together so that I only need 3 workers. You have to check all the dependencies hold true. We know the critical path, the dependencies work there. D happens after B, so it's fine to have it after B. G happens after D, so it's fine to have it after that. And E happens after B, which happens in this picture. So the scheduling is fine there. Now, one little formula for you to remember. This is a useful formula. Let's rub this out right now. If you want to work out the lower bound for the number of workers, now what does the lower bound mean? The lower bound means it's the minimum number of workers to complete the project that's possible within its critical time, That means you could not do it with any number of workers lower than that. So it's a lower bound for this. Now, the number you might find doing your scheduling diagram might be bigger than this because of the various overlaps, but this is just potentially the one that you might be able to get the lowest possible one. And how you work that out, it's your sum of all your activities, so it's your sum of activities divided by the critical time of project. So in this case, the sum of all the activities, well, we have 7, and 3 is 10, add 4 is 14, add 6 is 20, add 10 is 30, add 5 is 35, add 7 is 42, and add 8 is 50. So the sum of all the activities is 50, and the critical time of the project, if you remember, the critical time is 0 to 26, so I would divide that by 26 as follows. And if I did 50 divided by 26, what exactly would I get? So 50 divided by 26, you get yourself 1.9. Okay, so this lower bound here would be the number of would be the smallest integer bigger than this, so it would be 2 in this case. So it is possible, in theory, it would be possible to do this with 2 workers, but given the overlaps and the dependencies, in this case the scheduling diagram showed that the actual minimum in our case was 3. You couldn't have done it better than 3, but the lower bound was 2. So given the numbers, maybe 2 was possible, but given the fact, the various floats and what depended on what, actually in this case 3 workers were needed, and that's the smallest. Okay, so here's another question. You may feel confident now and you may want to pause the video. This shows you the Gantt chart and it asks you to schedule the activities in the scheduling diagram in order to calculate the minimum number of workers. So pause the video if you feel like you can do it, otherwise I'll go through in 5 seconds. So let's try and schedule this. Now the first thing is, if we do a scheduling diagram, it's going to look similar to our Gantt chart. We'll just call it a scheduling diagram. And what I've got is 0 to 25, and I've got a long list of columns like that. Now obviously you're going to need a worker for the critical activity. So worker 1 is going to be the critical one. So I'm just going to draw that out very quickly. It's going to go 0 all the way to 25, and it's going to have the various elements. So A is going to be 0 to 8, C is going to be 8 to 16, G is going to be 16 to 21, etc. Okay, so we've got the activities A, C, G, and J, like that. Okay, so that's worker 1. Now let's think about assigning worker 2 to some jobs. So let's put worker 2 here. Now, in fact, before we do this, it would be a good idea to work out the lower bound. What's the possible lowest number? Okay, so what we've got here, the lower bound is the sum of all the activities. So all of these clearly add to 25. Add another 6 is 31. Add another 7 is going to be 38. Add 11 is going to be 49. Add a 10 is going to be 59. Add 3 is going to be 62. And add 4 is going to be 66. So it's going to be 66 divided by the critical length, which is 25. Okay, and if we did 66 divided by 25, what would we get? Just going to get the calculator. So 66 divided by 25 is 2.64. So 2.64. So it's the lowest integer bigger than this. So our lower bound is going to be 3. So we know we can't solve this problem with less than 3 workers. We may need more depending on the overlap, but we know we can't solve it less than 3. So that gives us a good indication. So let's do B. Let's put B between 0 and 6. Why not? There's nothing. So B goes between 0 and 6. That makes sense to try that. Now D, E, F, H or I could go next. Any one of these. So I'm thinking it's probably best to do D because I think F might seemingly fit after that. So I'm going to do D next. So I've done that one, that one, that one, and that one. I've done that one. I'm going to put D next between 6 and 13. So D is going to go next between 6 and 13 as follows. And I've done that one. Now E. E is going to need another worker because E can't fit after D at all. So E is definitely going to need another worker. So we know we're going to need worker 3. Okay, so we'll come back to E in a second. What about F? F could be shifted over 1, 2, 3, 4, 5 places. So 1, 2, 3, 4, 5. So it could start here. So it could fit perfectly after D. So I'm going to put F after D because that makes sense. So F's going to start at 13. And it's 10 long, so it's going to go all the way up to 23. As follows. And I'm going to call that F. And what else can I fit in here? I've only got a space for two more spaces here, whereas that's 3 long, that's 4, so we can't fit H and I there. So that's going to be worker 2. So what we need to finish off, we need to finish these 3 guys off there like that. And what we can do is we can obviously assign worker 3 to E. So I'm going to start at 6 and I'm going to end at 17. So start at 6, I'm going to end over there at 17. This one here, H and I have got to happen. So I'm going to keep H where it is and maybe shift I over like that. Okay, so I'm going to shift I over. So keep H there, starting at 18 and ending at 21. So starting at 18 and ending at 21. And I'm going to move I over 3 places, so it starts at 21 and ends at 25. So it starts at 21 and ends at 25, would be something like that. And these would be my activities E, H, and I. And it just so happened in this case we got 3 workers, which was like our lower bound. So it worked out we could actually get to our lower bound number, but sometimes you might have to get a number bigger than that. So there's our scheduling diagram showing how we would distribute our workers. Okay, the last one, again, here's another question. You may want to pause the video, read through and have a go. And I'll go through in 5 seconds if you need to check your work or just need guidance through the question. Okay, so this question, this is the information you're given. The cascade chart on the following page represents the project with a critical time of 22 hours. The reason that's critical time, these are clearly the critical activities, and in total they take 22 hours. It says, given the total duration of all 64 activities, if you add up all of these activities, it's 64 hours. Calculate the lower bound. So the lower bound, we've done that a few times. The lower bound is going to be 64 divided by 22. And if you were to do 64 divided by 22, you get yourself 2.9. So you get yourself 2.9. So the lower bound's the smallest integer bigger than this. So the lower bound is 3 workers. So in theory, it might be possible to solve this sort of problem with hours with 3 workers, but obviously it's going to depend on how things overlap, etc. So we may have to use 4, etc. So that's part A done. Part B, an unforeseen problem means that activity B cannot be started until 2 hours into the project. And it says, does this mean that the time for the whole project is actually delayed? Okay, well, if you look at activity B here, which is this one, activity B is not a critical activity, so it's not critical. So if it has a slack or a float of 3, so if it was delayed by 2 hours, that wouldn't delay the whole project. For this question here, maybe in a different coloured pen, is does it delay the project? I'd say no. I'd say activity B has a float of 3, so could be delayed 2 hours without delaying whole project. Okay, so that's what I do for part B. Then for part C, it says which activity must, so this must be happening at 17 hours into the project. So what I'm going to do is I'm going to get a line and I'm going to go down in 17 hours like that. Now, which activity must be happening? So, point you can see that well, you've just at this very moment finished F and you're just about to start J. So at that instant in time, maybe you could argue that no activity is happening at that very instant in time, but you can certainly argue that activity H is going on. So activity H. G doesn't have to fit there, E doesn't, and I could be shoved over here. Now, there is some debate as to whether you say J is going on at that time because you've just finished F. So I might put J in brackets to say, look, with it, like, you know, in an instantaneous moment of time, J is just about to kick off. But that's what the answer says in the book, but it's one of these two. Lastly, complete a scheduling diagram to complete the project and state the minimum number of workers. So the first thing we're going to do is we're going to assign worker 1 to the critical one. So worker 1 would be here. Okay, so it would go from 0 to 5, from 5 to 9, from 9 to 17, etc. So that would be worker 1. And then we think about what to do next. Now, B or C, you can see that you're going to need 2 more workers because B and C can never happen at the same time, because no matter where you shift B along its possible flow, or C, you're going to need a different worker for each. So B, I'm going to start B off there, 0 to 6, and I'm just going to, as it is, start off C here from 0 to 9. Like that. So I'm immediately realizing that I'm going to need new workers. So I'm going to put worker 2 here, and I'm going to put worker 3 here. This was A, D, F, J, and this was B and C. Now, so I've done this, 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 and this. Now, E's next. Where am I going to put E? Well, I may as well, I could put E either with B or C. It doesn't really matter. So what I'm going to do is I'm going to, why not put E and G with B and C, so it doesn't really matter. So E, I'm going to put E here starting at 9 and ending at 16, so starting at 9 and ending at 16. and I'm going to do the same thing with G, starting at 9 and ending at 16 here, like that. Okay, so this here is going to be E, and this is going to be G, like that. So I've done that and that. Now H is next. H, no matter where I've shoved E, A, G, etc., H has got to have another worker, because H could only be shifted along 2. So that's going to need its own worker, and I'm going to put its own worker here from 9 to 20. So from 9 to 20 is another worker here for H. So I'm going to actually need worker 4 here. Now the last thing is I. Can I fit I anywhere? Well, I could put I up here with either G or E, it doesn't matter, rather than shove it for a new worker. So I could certainly put I up here, and I'd have it starting at 16 and ending at 19. So starting at 16 and ending at 19, and that would be I, like that. So I need 4 workers here. Even though my lower bound was 3, the number of workers required for part D was 4 workers in order to complete the project. That's all that's required for this video, and we have completed everything you need to know on critical path analysis. Just one tiny tip, it didn't really come up, but look in the exam questions. I'll do a few exam questions about it. Make sure when you're designing your scheduling activities, if there is an initial activity network, you check the dependence at the end. But I'll do that in an exam question at the end. Thanks those for watching.